Welcome back. Today I will say ring theory, and today I will say ring theory just as a review, because in the previous video I had seen one lecture series about ring theory. Today I will discuss ring theory just as a review. Just as a review, today I will again discuss ring theory, but at first I will hardly recommend you, if you don't see my previous video, then see the playlist of my channel. I had defined today's topic elaborately in my previous video. Today I will discuss just as a review some more examples, some more concept about this theory. Today's topic is, today I will say what is the ideal. We all of us know, I hope, because in my previous video I have defined this part elaborately. What is the ring homomorphism, quotient ring? We all of us know ideals are actually kernels of quotient ring and vice versa also. That means, since ideal are always kernel of quotient ring, that means ideal means there exists always one ring homomorphism which are actually the kernel of this ring homomorphism. In a ring, we all of us know we can add, subtract and multiplication, and ring is abelian group under addition. For a ring with identity, means the multiplicative identity. In ring, multiplicative identity may or may not be exist. Subring. We all of us know subring. Subring is closed under addition and closed under multiplication. Ideal also be a subring, but this is the stronger condition than the subring. Here the stronger condition is, obviously for ideal this is closed under addition, closed under multiplication, but the stronger condition is, we all of us know, this is the, if R belongs to the ring and A belongs to the ideal, that imply RA belongs to ideal and AR belongs to ideal. A be the member of the ideal means subring. If RA belongs to ideal means this subring, then this is left ideal, and if AR belongs to ideal, then this is right ideal. And when two ideal are equal, left ideal and right ideal both equal, then this is ideal. We all of us know this is. Just recall the idea of ring homomorphism. If there exists a mapping phi from R to R dash, which is ring homomorphism. Ring homomorphism means this is R dash, A map to phi A, B map to phi B, then by ring homomorphism A plus B always map to phi of A plus phi of B, and AB map to phi of A times phi of B. That means by ring homomorphism, we all of us know phi of A plus B equal to phi of A plus phi of B, and phi of AB equal to phi of A times phi of B. This is the ring homomorphism. And if we eliminate the multiplication part, then actually this is the ring homomorphism. Means phi from R with respect to addition to R dash with respect to addition, this is actually group homomorphism. So we all of us know, so ideals are kernel of ring homomorphism, and each ideal produces a nice partition, which is actually the idea of quotient ring. It divide nice quotient, which I will see in my few minutes later. Phi kernel is ideal. Consider this ring homomorphism phi from R to R dash. Obviously, kernel means set of those elements A in the ring R such that phi of A equal to 0. Then we have to prove kernel is an ideal. For this, if A belongs to ker phi and R belongs to the ring R, that implies RA belongs to ker phi. We have to prove this. Since this is the ring homomorphism, so phi of RA means, by the definition of ring homomorphism, this is equal to phi of R times phi of A. And since A belongs to ker phi, that means obviously phi of A equal to 0. That means, and R belongs to arbitrary element of the rings, so phi of R would be something. Then phi of R times 0 equal to 0. That implies RA belongs to ker phi. So, since here the R is arbitrary element of the ring and A belongs to ker phi, and I have got RA belongs to ker phi, that means our proof has done. Ker phi is an ideal. Similarly, this is ideal because if we multiply RA from left side also, this is also would be 0. That means AR also belongs to ker phi. So it is actually both side ideal. So this is ideal. So ideals are actually kernels of ring homomorphism. Also, ideal means always there exists one ring homomorphism which be the kernel of this ring homomorphism. Now consider this ring and I is this set. Here R contain the matrix which contain AB0C, where ABC belongs to R. Obviously this set is a subset of M2 cross 2R, and I equal to set of those elements 0x00 where x belongs to R. Now my question is, I is a ideal? For this, consider one mapping phi from R to R cross R. Obviously R cross R means set of those elements x comma y such that xy belongs to R, and the mapping is such type phi of AB0C equal to AC. Obviously this type of mapping is a ring homomorphism because consider this is A and this is B. Then phi of A plus B equal to phi of A plus A dash, B plus B dash, C plus C dash, here 0. And by this construction mapping, this is equal to A plus A dash, comma C plus C dash. And this means this is equal to A comma C plus A dash comma C dash. Therefore, this implies phi of A plus B equal to, because this is phi of A and this is phi of B, phi of A plus B equal to phi of A plus phi of B. Similarly, phi of AB equal to phi of A means this and B means this. This is equal to phi of AA dash, AB dash plus BC dash 0 CC dash. And by the constructing mapping, this means AA dash comma CC dash, and AA dash comma CC dash mean we can write this as A comma C, A dash comma C dash, and this is actually phi of A and this is phi of B. Therefore, phi of AB replace phi of A times phi of B. So, this type of mapping is actually ring homomorphism. Now, since this is the ring homomorphism, therefore what is the kernel of this ring homomorphism? Kernel is phi of AB0C equal to 0 0 0. Here that imply phi of this means A comma C equal to 0 comma 0. That imply A equal to C equal to 0. Equal to C equal to 0. Therefore, kernel of this ring homomorphism would be, since A and C both 0, car phi equal to set of those elements which contain 0 B 0 0 where B belongs to R. In the question, is this matrices is ideal? Since I have constructed one ring homomorphism and in which I is the kernel of this ring homomorphism, so obviously this I is an ideal. This is the one way to prove one subring be ideal or not. Find such homomorphism for which the ideal would be the kernel. For any ideal, always there exists one homomorphism for which this ideal be kernel. Now I will say the idea of quotient ring. In my previous video I had seen the idea of quotient ring elaborately. Today I will discuss this part just as a review, similar to before. Consider a mapping phi from R to S, which is ring homomorphism. Then car phi obviously map to 0. Here this is R and this is S. That means then other element of this ring R is A plus car phi, B plus car phi, C plus car phi, so on. And A plus car phi map to phi of A because car phi map to 0. So this is the phi of A. Similarly B plus car phi map to phi of B. And this is actually R mod car phi. That means actually this is the set of coset in the quotient ring because this is the idea of the quotient ring. And here the operation would be such type: A plus car phi times B plus car phi would be AB plus car phi. Similarly, A plus car phi plus B plus car phi would be A plus B plus car phi. Here the operation would be such type. This is the actual picture of quotient ring. That means this is actually set of coset of car phi. I hope my all viewers have understood this concept easily. Now I will say one example. Consider one mapping psi from Zx to Z, and the mapping is such type f of x map to f of 2. Then kernel of this mapping is such fx in Zx such that f of 2 equal to 0. Kernel is such type means, just recall, in Rx, if alpha belongs to R and Gx belongs to Rx, then we can divide Gx by x minus alpha. And when we can divide Gx by x minus alpha, then the remainder would be G of alpha. Therefore, since here kernel is set of those fx in Zx such that f of 2 equal to 0, that implies set of those function fx such that fx is divisible by the polynomial x minus 2. And when fx is divisible by the polynomial x minus 2, then the remainder part would be 0. And since fx is divisible by the polynomial x minus 2, then this would be such type: x minus 2 times hx, where obviously this hx belongs to Zx. Because kernel of this mapping is such fx which is divisible by x minus 2. So kernel of this mapping would be such type. Obviously, just check it own self. This type of mapping is ring homomorphism, and this type of mapping I have defined my previous video. So I have told you, if you don't see my previous video of ring theory, at first see the playlist of my ring theory chapter and see the whole video. Then this video would be so easy, because today's topic is just as a review topic. Therefore, since this is ring homomorphism and this is the kernel of this ring homomorphism, that means obviously this is ideal. Then the mapping would be such type. Just see the picture. At first think oneself how look like the mapping. Here the mapping is zx to z and the kernel is such fx such that f of 2 equal to 0. That means actually idea is set of all coset of this kernel is actually isomorphic to set of integer. I hope my all viewers have understood the picture of quotient ring. Why here zx mod psi is isomorphic to integer. I hope my all viewers have understood this picture easily. Okay? Well, now I will see one ring homomorphism which is qx to q square root of 2 and the mapping is such type fx map to f square root of 2. That means here such fx whose root is square root of 2. And obviously kernel of this f is such fx which is multiple of x square minus 2. Actually this is ideal generated by x square minus 2. That means since this is ring homomorphism and kernel of this ring homomorphism is this, so obviously this is ideal and we can tell qx ideal generated by x square minus 2 actually isomorphic to q square root of 2, because here the coset is look like a plus bx plus x square minus 2 times f of x. After putting the value square root of 2, this would be a plus b square root of 2 plus this is the member of kernel of f, so this is obviously would be 0, that and this is actually isomorphic to q square root of 2. So this coset is actually isomorphic to q square root of 2. I hope my all viewers have understood this is clearly. Okay? Oh, this type of concept actually very important for higher study. Now I will see, here I have used one notation, ideal generated by x square minus 2. This is mean actually same like cyclic group. Cyclic group generated by A means this is the multiple of A. Here I have used this same like cyclic group. Here this notation actually ideal generated by x square minus 2. Actually this is the smallest ideal that contain x square minus 2. That means there exists other ideal also, but this is the smallest ideal. As for example, in zx, ideal generated by 2 comma x. Ideal generated by 2 comma x. This is means actually all polynomial who is from 2p plus x cube, where this p and q are polynomials with integer coefficient. That means they are exactly set of polynomials with integer coefficient where the constant term is even. That means ideal generated by 2 comma x means set of those polynomial with integer coefficient, because here the ring is zx where the constant term is even. Now if we consider such mapping psi from R to R mod I such that psi of A equal to A plus I, obviously this type of mapping always ring homomorphism, because psi of A plus B, by definition, this is equal to A plus B plus identity, and this is equal to, by the definition of quotient ring, A plus I plus B plus I, and this is equal to psi of A plus psi of B. Here B. And psi of AB equal to, this would be AB plus I, and by the definition of quotient ring, this is equal to A plus I times B plus I, and this is equal to psi of A times psi of B. Therefore, the property of ring homomorphism has satisfied here, and in this mapping, the multiplicative identity is psi of 1 equal to 1 plus I is the multiplicative identity of R mod I, and kernel of this mapping is such type A belongs to R such that psi of A equal to 0, and this is 0 in R mod I. That means, since R mod I is 0, that means psi of A equal to 0 plus identity, and A belongs to R such that psi of A equal to 0 plus identity in R mod I, and psi of A means A plus I equal to 0 plus I, that imply A belongs to R such that, since A plus I equal to here 0 plus I, that imply A belongs to I. Therefore, since A belongs to I, that means kernel of this mapping is this ideal I. So, I hope my all viewers have understood how look like this mapping when psi map from R to R mod I. Okay? OL. Now I will see Rx modulo ideal generated by x square plus 1 is isomorphic to C, complex number, because for this those effects which is multiple of x square plus 1. That means this is actually ideal generated by x square plus 1. Then Rx modulo ideal generated by x square plus 1 is isomorphic to C, because here the element of coset is such type A plus Bx plus x square plus 1 fx, and here the mapping fx map to f of I. Just put the value I, then this would be A plus Bi, and this part would be, since this is the member of kernel of A, this part would be 0. That means image would be A plus Bi after putting the I. So this is isomorphic to complex number. So Rx modulo x square plus 1 is isomorphic to complex number. Okay. Now I will see another type of quotient ring C of xy, and I equal to ideal generated by x comma y, which is actually set containing the element p of x comma y times x plus q of xy times y, where pq belongs to C of xy. Now I will see Cxy modulo ideal generated by I is isomorphic to complex number. For this, since we have to find the C of xy, quotient ring ideal generated by I is isomorphic to complex number. For this, consider one ring homomorphism C of xy to C such that f of xy goes to f of 0, 0. I have considered this ring homomorphism for this ideal because here the ideal generated by xy. That means for this ring homomorphism, we can tell this is actually kernel of F of this ring homomorphism, because then kernel of this ring homomorphism is set of those xy such that f of xy map to 0 0, and f of xy map to 0 0 means obviously such polynomial whose contain x and y, means p of xy comma x plus q of xy comma y, and this is actually ideal generated by x comma y, and which is actually our given ideal I. Therefore, the quotient ring C of xy modulo I means obviously the set of coset would be such type A plus IB plus ideal generated by x comma y, which is equal to A plus IB plus P of xy times x plus Q of xy times x. Okay. Now, since here the mapping f of xy goes to f of 0 0, so after putting the value f of 0 0, I will only get A plus IB, because this part would be 0 when I will put the f of 0 0, and obviously this is isomorphic to C. So C of xy modulo ideal generated by x comma y is isomorphic to complex number. I hope my all viewers have understood this type of quotient ring. This type of quotient ring actually very important for higher study. I will say another type of quotient ring, Z2x modulo ideal generated by x square plus x plus 1. Obviously, this is isomorphic to F4. And F4 means actually field containing 4 elements. For this, consider one ring homomorphism from Z2x to F4. And the mapping is such type f of x map to f of x modulo 2. And ideal generated by x square plus x plus 1 is actually fx times x square plus 1. Then Z2x modulo x square plus x plus 1 means actually the set containing the element 0, 1, x plus 1. And obviously this is isomorphic to F4, means field of containing 4 elements. Similarly, if we consider Zn x modulo the ideal generated by x to the power n, x to the power n minus 1, so on, this type of quotient ring would be isomorphic to Fn. I hope my all viewers have understood this type of concept easily. How look like the quotient ring? This type of quotient ring actually very important for higher study. Okay? All of us know Fn means actually the field who is containing n elements. So, every quotient ring Zn(x) modulo x to the power n plus x to the power n minus 1, so on, this is always isomorphic to Fn. I will stop here. In my next video, I will discuss this type of concept elaborately. Actually, this type of concept very important for higher study. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.